So for those of you who are interested in a midterm replacement essay project, definitely shoot me up. I've gotten a couple requests. If you sent me a message and I haven't responded, let me know. Right, but I want to just make sure the offer is open to everybody. Okay, so quick thing on the homework, right? Just a couple quick announcements. So question 1 should be very straightforward, just basically straight calculation. Question 2 and 3 are not as difficult as people as some of you are making it out to be, right? Especially question 2, right? If we just pull up. Oh, I really want my external monitor to be working so I don't feel so cramped. And I have a spot off screen to put the chat and stuff. Okay, so essentially this is just a question, an interdiffusion question, right? Where I give you the interdiffusivity and I give you the concentration gradients, right? And the velocity of the markers, right? And it's basically just asking you to find the intrinsic diffusivities, right? So we know that, right? This is the velocity, right? From Darkin's first equation, right? So here we have the diffusivity of A and B. And then we have this equation here, right? Where this is just the definition, right here. Here's the definition of the interdiffusivity, which is given. You know the mole fractions, right? So it's just a fairly straightforward solve 2 equations with 2 unknowns, right? Then for question 3, right? I don't have it up here. Hold on. Let me open the previous. Right. So come on. Right. Okay, so if we look here, this is for vacancy diffusion, but I'm asking you about the ionic compound sodium chloride, right? And so the relevant defect that mediates the diffusion is going to be a Schottky defect in this case, rather than a vacancy in a metal alloy, right? And I give you the D naught term. So for the first part, I give you the diffusivity and D naught, and I just ask you to calculate the activation energy. All right. For part B, is just a tiny little bit more complicated. I ask you to estimate the value for D naught, right? So if we look here, Q is this part here, right? And that just comes from our enthalpy terms, which I give you. And then D naught is all this stuff out front, right? So what I want you to do is just put everything together into here, right? And notice that I even make it fairly simple and give you the formation, the entropy terms in units of R, right? So that it cancels nicely for you. So don't make it too complicated. This was meant to be an easy assignment. Don't get lost in the weeds thinking about it too much. Right? Okay. So
I will never underestimate my ability to make it harder.
That's a general truism in life. Right? Overthinking things and making the simplest possible stupid mistakes, right, is a hallmark of being human. Right? My capacity to mess up simple things is infinite. Okay, so let's go through some new science. Right, so today I want to talk about sintering. There's going to be some reading going up, and the reading that's going up is from this book, Fundamentals of Ceramics. The reading, I'm going to say the reading is this text is truly really a graduate level text, so the level of the reading is difficult. I don't want you guys to get hung up on that, right? You'll see the lecture is largely qualitative, because what I want you to what I want the takeaway is a simple physical picture of what's happening, right? The models for sintering are all very complicated, and there's lots of stuff going on, and there's lots of mechanisms going on. And the takeaway is it's incredibly difficult to be at all quantitative. I just want you to think about what mechanisms might be operating under what conditions, and whoa. I figure out how to make it small again. There we go. No, the reading will be uploaded to Carmen, right? I'm not going to make you buy a $150 book for one half of one chapter. That would be criminal of me. So yeah, so 3D, not specifically metal 3D printing, but this is very relevant physics to 3D printing, and I'll point it out where. So selective laser sintering and selective laser melting. So, okay. So let's go on. Okay, so metals and polymers, right? We talked a lot about molten processing, right? Because we cast them, weld them, and then machine them or forge them into the final desired shape. With ceramics, that's much, much more challenging, right? So they're refractory, meaning they don't melt till very, very high temperatures. The fusion temperatures are just way too high, with the exception of silicate glasses that can be worked with easily in their molten state. And they're way too brittle to do any, most of the time, machining or forging into a final shape. So that means we need to deal with ceramics, we need a completely different processing route, right? So instead, things are sintered. So we start with fine powders that are milled and then mixed and molded into a desired shape, right? Pressed into a green body is the term for that preform. And then they're heat treated or fired to convert them to dense solids, okay? And so there's really important applications for metals, right? So powder metallurgy, that nickel superalloy turbine discs are formed by a powder metallurgy route where you mix powders into a form and then it's hipped by hot isostatic pressing. Additive manufacturing, not addictive manufacturing. So laser powder bed fusion, right? We have a example. We have a combination of melt and solid state fusion, but then these parts are usually hipped to close up any porosity, right? And sintering and grain growth are intimately related. So when we talk about grain growth next, we'll see how closely it's related to what we see in sintering. Okay, so what exactly is sintering? So Herring in 1950 basically said sintering is any change in shape which a small particle or cluster of particles of uniform composition undergoes when held at a high temperature. Not a particularly useful working definition, but useful for understanding what's going on. We've got some small group of particles, and under heat, they're going to change their shape. And most of the time, we're going to be talking about changing their shape without melting. Okay? So sintering, from a more practical definition, I got to work the hot end on mine. Something's going on. I tried to print something with my son the other day, and I've got a partially clogged nozzle that I can't get unclogged, even with needles. So let's see. Oh yeah. So sintering is the process. You can tell I'm really tired because I'm having a hard time keeping focused on what I'm doing. The chat's too much. The chat is too interesting. So sintering is the process by which we make a dense ceramic or metallic body on heating from a powder compact. Okay, so sintering is a really complex phenomena, right? There's a lot of mechanisms happening and processes occurring simultaneously. Liquid phase sintering occurs when some components in the powder compact melt and wet the surface of other components. And then I say here, solid state sintering is more common and occurs without any melting. I should clarify, almost all commercial sintering processes do in fact have some liquid phase. But from a purely physical and materials point of view, right, the types of things that as material science we study, solid state sintering is more common. So this could be a little confusing. Okay, so what exactly is happening during sintering, right? So in solid state sintering, we're going from a loose or a tight agglomeration of powders to a well-defined structure that is dense without any porosity. And notice that we have a volume change, things shrink, right? In liquid phase sintering, we have some component that melts and wets everything. And we have some shrinkage, but not quite as much, right? So these are the primary differences. We're going to start with solid state sintering, right? So here we have Nanocorundum, right? So what's corundum? Right? It's aluminum, or essentially alumina, right? But it's not pure aluminum oxide. It's got some other minor stuff in it. But anyway, we've got this is a 500 nanometer scale bar, right? So these are particles that are less than 100 nanometers, so a very fine ceramic powder. It's then pressed and heated to 1285 C at atmospheric pressure, and we get something that's over 99% dense, right? And notice that the grains are all significantly larger. The grains are a little less than a micron, and we started with an average particle size of 80 nanometers, right? So the grains themselves have increased by about a factor of 10 in size, right? Meaning that more than one particle has formed into a grain, right? So today we're talking about how do I go from the powder to a solid compact. On Monday, we're going to talk about how these grains grow, right? And in reality, the process happens in parallel, okay? So this is solid state sintering, right? How do we know? We don't see any hallmarks of melting, right? We don't have a film of a second phase around the grains, right? And when we look at liquid phase sintered products later on, we'll see that there is a clear difference. So why has the grain size increased? This is something you guys know intimately already, right? It's the reduction of surface area, right? This fine powder, there's a lot of ceramic air surface, right? And even though the ceramic, this grain boundary energy, depending on the system, could be higher or lower than the ceramic atmosphere surface energy, we now have a lot less of it, right? Remember, volume goes by cubed, surface area goes by squared. So if we make the increase the radius by an order of magnitude, we've decreased the surface area by a factor of 100, right? Which is a huge energy decrement, right? Even though the actual surface areas and the driving forces are quite small. So let's talk about solid state sintering, right? So there's two competing mechanisms that we have, right? That can lower energy. We talked about coarsening before, right? When we talked about our surface area and we talked about Gibbs-Thompson, we basically said that the small particles are going to coarsen, and the largest particles will grow and eliminate the smaller, right? So that's one mechanism. The other mechanism is essentially sintering, right? Where we have our powder compact that is going to densify, and then the grains are going to grow. Okay, so we need to make sure that we're in a regime where this happens, and not we just have a bunch of small, a compact of small particles that become big particles, but don't agglomerate together to make a fully dense ceramic. Okay, so here we see coarsening versus densification, right? So right, in this case, it's looking at doped versus undoped. But anyway, the idea is these started with very similar, if not identical, powder sizes. They were sintered for the same amount of time. But here we got a very dense compact. Here we just, our particles coarsened, and now we have huge pore spaces. Okay, so depending on the end goal, one might be preferable to the other. Right? Obviously, if you want something structural, you want this. But maybe you're doing a bioceramic, and most of the time you'll have a different processing route than sintering. But if you want something like, say, a water filter with a controlled pore size, right? A densification route is what you want. So how do we control the balance between these two things, right? These are very different end states, right? And it's all about control of processing conditions, right? So let's look at what the local driving force for sintering is, and then think about how do we control our processing conditions to pick the mechanism that we actually want. Okay, so this is all about our good friend Gibbs-Thompson, right? So the curvature of the surface is going to cause local variations in the partial pressures and the vacancy concentration. Another way of saying that is the local curvature is going to make changes to our local chemical potentials, right? And so at different spots in our powder, we're going to have a different driving force for atoms to leave where they are and go somewhere else, right? Okay, so remember that partial pressure over a convex surface is higher than that over a concave surface, and that the vacancy concentration under a concave surface is higher than that below a convex surface, okay? But in either case, we have a driving force that is present that induces atoms to migrate from convex to concave areas. So atoms are going to go from mountaintops to the valleys, and vacancies are going to go from the valleys to the mountaintops, right? So the local driving force for this is quite small, on the order of joules per mole. Okay, so let's take a look, right? Just remember our Gibbs-Thompson review, right? And if we have this atom here and we look at how easy it is for an atom to leave the surface and go into the air as vapor, right? It intuitively should be clear that we're much more likely in P3, right? This atom has much less confinement on it than, say, this atom down here, right? So the partial pressure above this convex surface is going to be higher, easier for atoms to leave, right? And the vacancy concentration is going to be greatest under here. Okay, so we have our vacancy concentration, right? Okay, so we have a bunch of different mechanisms, right? So if we're trying to think about sintering, we need to move atoms from one part of the particles to the other to achieve the aim of either densification or coarsening. Okay, so what mechanisms do we have available to us to transport material? Well, we've got quite a few. Okay, so we can have atoms that evaporate from the surface and recondense on the neck. Remember, the partial pressure over here over a convex surface is going to be higher than a concave, right? So atoms can selectively evaporate here and recondense here. Okay. We also have surface diffusion, right? We can diffuse along the surface to the neck. Okay. We have these are, oh, no, it's not. I can't read. So we have bulk diffusion. So we take atoms from the surface, but instead of them diffusing along the surface, we diffuse through the bulk to the neck, right? The region where two particles meet, right? We can also have grain boundary diffusion from the particle interiors to the neck. And then we can have bulk diffusion from the grain boundary to the neck. And then we also have viscous flow, creep, or deformation plasticity, right? Which are not shown. What's important to remember is that all 6 of these mechanisms are happening simultaneously, right? But the overall microstructure evolution is going to be dominated by whichever one is operating the fastest. So we need to set a pressure and temperature range to select the mechanism or mechanisms that's going to give us the final microstructure that we want. Right? So if we want densification, which subset of these can we choose? What needs to happen to densify our particle? Or densify our powder compact? Right? Oh, I put this out of order. Hold on. So this is our viscous flow, right? So these are glass phases. So we do essentially, because of the chemical potential changes, we get highly, excuse me, been talking too much on Zooms. We get highly local melting, right? And then we have the particles are held together by liquid capillary pressure. And then we have an applied force and we get viscous flow here. So this is this really isn't liquid phase sintering. It's kind of like this intermediate. And this happens a lot with glass beads and things like that. Right? But it wasn't shown on the previous slide, so I just wanted to show the mechanism. Okay. So if we think about what we need for densification versus what we need for coarsening, I want you to think about this and realize that any mechanism in which the source of the material is the surface of the particle and the sink is the neck area won't lead to densification because the centers of the particles won't move closer together. Right? So if I have two spheres that are touching and I just go from the surface down, I'm not moving the center of mass of these particles closer together. However, if I move material from the neck, from the grain boundary here to the neck, I'm removing material from the region between the center of mass of my two particles and pushing it out. So that means these two particles have to move closer together, right? Leading to densification, right? So that means evaporation, condensation, surface diffusion, and lattice diffusion from the surface to the neck are not what we want if we want to make a dense compact, okay? They are going to change the shape of the pores, growth in the neck. You're going to have a increase in the compact strength over the green body, right? But you are not going to have a fully dense ceramic if these are the materials that are operating. The same thing in metals, right? If I am hipping a powder metallurgy sample or trying to close pores in an additive manufactured part, I am not going to be able to remove those pores by these mechanisms, okay? So for densification, I need to move material from this shaded area out into the neck. And when I do that, my particles come closer together and my compact shrinks. Okay? So how is this possible? Well, remember, there are going to be more vacancies in the neck area, right? Because I have a concave surface. So I have a higher vacancy concentration here, right? Which for ceramics translates to higher Schottky or higher Frankel defects, depending on what we have. But if I have a straight metal, then I can just think about single vacancies, right? So if I have an increased vacancy concentration here, it means I also have a increased diffusivity, right? Right? What is the source for my vacancies? Right? I have to generate them somehow. Right? So if I have vacancies that are formed at the surface, then they come to this grain boundary area here to be annihilated. That means I have a net flow of atoms from this grain boundary area to my neck. And so I have mass transport, net mass transport out of this middle region to the sides here, and my compact is going to shrink. Okay? And notice that when I do this, right, this doesn't exist in isolation. These particles are all packed together, meaning that as I do this, I not only move these particles close together, I'm adding atoms into the pore space. Right? So that's my primary mechanism. So what does this look like? I start with particles that are stuck together. And as sintering starts, I have neck growth that forms. And eventually these I keep moving atoms into my neck region. And eventually I end up with these polyhedra type, my particles become polyhedra that are stuck together with continuous pore channels along the edges of this polyhedra. Okay. Then if I keep going, these faces are going to keep growing out, and eventually I'll close my pore channels along the edges of this polyhedra, and I'll only be left with pores at the vertices. Right? And if these were ideal flat polyhedra, which they're not, I'll have little tetrahedral pores at the corners. Of course, these are real interfaces, so they're going to adopt a curvature on their own, right? And that's important, and we'll see, right? But this is a really good physical picture model of what's going on here. Okay. So this is broken up into stages, right? We call this initial stage, intermediate stage, and final stage hardening. So the initial stage is the interparticle contact area increases by neck formation, and the contact area increases from 0, just tangentially touching, to about 20%. And the relative density is going to increase from about 60% dense to 65% dense. Why do we start at 60%? Well, because that's about what you can get from non-ideal packing, right? We're not putting the particles in close packed, right? We don't have microscopic tweezers to arrange these particles in a perfect arrangement, right? So we have to go by the limits that we get from packing powders into a container, right? Which means we're at about 60% density. Okay. The intermediate stage is where our continuous pore channels that are aligned with the grain edges begin to shrink, and we start to close those off, and those give us a big increase in density from 65% dense to about 90% dense, right? And this is where we're diffusing material towards the pores and vacancies away from the pores, right? In our final stage, our pore channels are pinched off, and we're left with individual pores that can either be lenticular if they're on the triple line of the polyhedra, right? So we don't pinch this off completely. Instead, here we end up with a little lenticular shaped pore or elongated pore that's still along this grain boundary. And at the corners, we have these tetrahedral type pores. Okay. It's at this point, this final stage, where these grain boundaries then become much more mobile, right? Because we're not essentially pinned by these pores anymore. And then we start to get really significant grain growth, right? So remember, why would the presence of these channel pores inhibit the grain growth? It's an energy thing, right? If this grain grows, our pore has to move from a triple line where there's lots of free volume to the inside of a grain, right? And that's just an energetically unfavorable situation. So the grain boundary, the grains are not really going to grow significantly until we enter the final stage of sintering, and we have these isolated pores that are not exhibiting a large retarding force on the motion of these grain boundaries. Okay. Now you can see why I say sintering gets very complex, right? Because we've got all these mechanisms operating in parallel. They're all complex, time-dependent diffusional processes. And a quantitative analysis is just going to be completely beyond the scope of what I want you guys to know, right? So just keep in mind the simple physical pictures and the general trend. Okay. So what are these general trends and mechanisms? Well, the activation energies for surface, grain boundary, and lattice diffusion increase in that order. Surface diffusion is the easiest, then grain boundary diffusion, and then lattice diffusion. Okay? So therefore, surface diffusion is going to be favored at lower temperatures, and lattice diffusion at higher temperatures. Do we have a way of creating densification by surface diffusion? No, right? For surface diffusion, we need to move atoms from the grain boundary to the neck. Okay? So anytime where surface diffusion is active, we're going to favor coarsening rather than densification. So we can say that at lower temperatures where surface diffusion is dominant, we're going to coarsen. Okay. Grain boundary diffusion and surface diffusion are preferred over lattice diffusion for smaller particles. Why is grain boundary and surface preferred for smaller particles? Well, because we have a lot more grain boundary area. And we have a lot more surface area in the original powders. Right? Our surface area the fraction of particles at the surface are going to be much higher. And then once things start to come together during the intermediate stage, we're going to have a much higher fraction of our atoms are going to be at grain boundaries. Right? So for smaller particles, for smaller powders, we're going to have an increase in grain boundary and surface diffusion. Okay. Lattice diffusion or bulk diffusion is going to be favored at longer sintering times, higher sintering temperatures, and larger starting particles. Okay. So if we are fully in the solid state, these are the diffusion processes that we need to balance. So we need to know what the activation energy for all of these different diffusion mechanisms are to be able to decide what temperatures we're going to be looking at. Okay. Viscous sintering is going to be the most forgiving mechanism with respect to particle size. Okay. And so these general trends are important, not just in initial stage, but also in intermediate and final stage sintering as well. Okay. And I think we're going to wrap up there for today, right? We'll finish this off maybe the first 10 minutes or so of Monday, and then we'll talk about grain growth, right? Because what we're seeing here is highly relevant to understanding how the pores are eliminated is directly related to grain growth. So no, not only grain boundary diffusion, you can also have bulk diffusion from the area between the particles to the neck, right? I can either diffuse along the grain boundary between these two particles, or I can have bulk diffusion from this interparticle area to the neck, right? Remember, we have an increased vacancy concentration here. So with the higher vacancy concentration, bulk diffusion is going to be enhanced in this region versus in the middle of our particle here. Right, because here we have this concave surface, whereas out here we have a convex surface. So it's not just along the grain boundary, but you can also have bulk as well. Right? So have a good weekend, everybody. Stay safe, stay healthy, and we'll see you on so the melting temperature in polymers is just too low, and diffusion of polymer chains is too hard. So sintering does not really apply to polymers. All right. So we haven't talked about polymer diffusion, but you can imagine how difficult it is to diffuse long chains past each other, right? So the activation energy for diffusion is just too high. Okay. Take care, everyone. Have a good weekend.